Okay, so now let us continue the discussion further. So now we have looked at the coherents, we have also looked at the podents, we have looked at crown ethers, which are very special cases of coherents. Now let us look at the other types of ligands in which host gas complexation behavior has been studied. Now once it was realized that a cyclic arrangement actually provides stability and encapsulates cations very efficiently, the next thing was whether we could make more rigidified host and even enhance further the binding constant associated with host guest processes. So in this regard, after Pedersen's work, there was a French scientist called Jean-Marie Le, who was there at the University of Strasbourg in France, and the University of Strasbourg in France, and he wanted to now make, synthesize and design three-dimensional host molecules which are of a bicyclic nature. So the crown ethers were just having one cyclic loop. He wanted to further derivatize it and make bicyclic host and 3D host molecules which are more pre-organized and which can effectively encapsulate the metal ion such that the metal ion is effectively hidden into the cavity which is created by this three-dimensional host. So instead of having a cyclic host which is more like two-dimensional, you now have a three-dimensional host. The metal ion goes and sits inside and it effectively encapsulates it so that it is hidden inside that particular cavity which is created by the host. And this process of the metal ion being hidden is referred to as kryptos in Greek, and hence came the word cryptands. So the cryptands comes from the Greek word kryptos, which essentially means hidden, where when a complexation takes place, the metal ion is effectively hidden inside the cavity which is created by the three-dimensional host. And the first cryptand which was synthesized by Jean-Marie Le is referred to as the 222 cryptand. And this is a very, very important compound because this 222 cryptand is sold commercially under the name cryptofix. So it has got a commercial name associated with it. And it has also been observed that this particular cryptand, in comparison to the 18 crown 6, encapsulates potassium ion much more efficiently, okay, and it is approximately 10 to the power 4 times greater for the cryptand in comparison to that of the crown ether 6 when the experiments are done in methanol at 25 degrees centigrade. So when done in this particular solvent at room temperature, it has been observed that the potassium ion binding for the cryptand is 10 to the power 4 times stronger than that of the corresponding 18 crown 6, and that is what also gives it a remarkable property, because a similar kind of ligand which is similar to that of the 18 crown 6 but having now a bicyclic nature instead of a cyclic nature can more effectively encapsulate the potassium ion and with a stronger affinity towards it. So the first thing was, how was the synthesis of these cryptands achieved? So the synthesis of the cryptands, let us look at the synthesis, which is very important because you need to synthesize these. So these started with, we looked at it in the last lecture where we took this particular cyclic host which has 4 oxygen atoms and then 2 NH groups, and we had derivatized this NH chemical modification of the side chain by replacing it with R. So now if we can again start from this cyclic ether, and we can first treat it with this particular reagent, which is the dichloro compound, and then under the principle of high dilution in 45% yield we get the corresponding NO, because now you see it is the the nitrogen lone pair which reacts with the carbonyl group, and then the chloride goes away, minus 2 HCl is eliminated, and then you have this thing which is N, and we can also have now this is the bottom part, and we can have the other one as well. As well as this particular one. So the nitrogen lone pair is there, here the nitrogen lone pair as well. So you can see here that this is N. So now we treat it with a reducing agent diborane and then do an aqueous workup. We get the corresponding cryptand in 95% yield, because this carbonyl groups is converted into the methylene group, and therefore we now get the corresponding cryptand. Let us see the structure of the cryptand, and we have this. And here we have now N. Okay, so we have this species now present with us, because so this is the carbonyl group which has been reduced. This is the carbonyl group which has been reduced to methylene, and we have the spacer. Now here you have got N is equal to 2 oxygen atoms. Here we have got N is equal to 2 oxygen atoms. We can now have a case where N is equal to 1. So then it is referred to as a 2-2-1 cryptand. And if N is equal to 2, it is referred to as a 2-2-2 cryptand. So we have two different cryptands depending upon whether N is equal to 1 or 2. So you can see that in this cryptand, it has now got a very rigid host, and it's a bicyclic host. Okay, you have two different cyclic rings. You have one here, and you have another one here, and the number of donor atoms is also more. In this case, the number of donor atoms is 5. In this case, the number of donor atoms is 6. So keeping this thing in mind, this discovery by Ley was very interesting, and many other cryptands have been synthesized using different techniques, and complexation behavior has also been examined in these as well. The next class of ligands is, now we see that Pedersen had discovered the crown ethers, Jean-Marie Ley has discovered the cryptands, and then came Donald Cram, who discovered spherands, and all these three people got the Nobel Prize in Chemistry in 1987 for this tremendous development in the field of supramolecular chemistry. So Pedersen, Ley and Cram, all of them got the Nobel Prize because each of them discovered a new class of chemical entities, a new class of host complexes which can effectively encapsulate guests, and later on we will see that there are a lot of applications of this phenomena. So then the concept was, now what was the hypothesis now proposed by Donald Cram. So what he wanted to do was further rigidification of the host. In addition to that of Charette effect, macrocyclic effect, macrobicyclic effect, he wanted to see whether further rigidification of the host can be obtained such that the donor atoms converge towards the central binding pocket. They strongly converge towards the central binding pocket even before the addition of the metal ion. This is because, keeping in mind that before the complexation takes place, the lone pairs have got a certain orientation, and after the complexation takes place, the lone pairs are forced to adopt converging binding sites. So there is an energy penalty involved. So what Donald Kramers thought, if we can even further rigidify the host by converging the donor sites even before the metal ion has started to complex, then it will display, it is expected to display excellent activities or affinities for certain metal ions only. For example, we have realized till now that sodium ion has been encapsulated by sodium, potassium ion has been encapsulated, but what about, say, small cation like lithium cation? It is very difficult to encapsulate lithium cation because the size of the lithium cation is very small, and you need a host which is having very strong converging binding sites such that once it effectively encapsulates lithium, it tightly holds on to it and does not release it, and this particular binding is preserved. So what he thought was that he needs to modify the host in such a way so that you have these converging binding sites which are already pre-organized, so before the metal ion complexation takes place or before the metal ion has been added. To keep that thing in mind, he designed a spherand. Let us now see the structure of the spherand here. So we have this, then okay. So this is a hexaphenyl host, but now we will see what are the changes here. So we will have this okay, and this one will be above, and this one will be below. Again this one will be 1 2 3 4 5 6, right? We have got 1 2 3 4 5 6, and we'll have this one, have this one, we'll have this one, and we'll have this one. So I think this should be alternate minus, so I'll just little bit So, okay, so then this one, okay, it's a bit difficult to draw, but what I would like to show you here is that, so we have got this hexaphenyl host. You will see here that these 3 oxygen atoms here, here and here, okay, I need to draw it, this one got rubbed off. Okay, so these 3 oxygen atoms you see are above the plane. So naturally, when these 3 oxygen atoms come above the plane, the corresponding methyl groups, they go below the plane. So this is the exposure of the 3 OMe groups, and then the Me groups are below. These ones here are below the plane. So these are below the plane, 3 oxygen atoms. 3 oxygen atoms are above the plane. The corresponding methyl groups are opposite. So the lithium ion can now come and sit here and form a nice octahedral arrangement. Form a nice octahedral arrangement. So lithium ion is now coordinated by the 6 oxygen atoms, and we know that lithium ion has got a strong affinity for oxygens. So lithium ion is effectively encapsulated such that you have got 3 oxygens above the plane coming from one side and 3 oxygens from below the plane. And what also happens is that when this encapsulation takes place, the outer part is lipophilic, or you can say hydrophobic. It is either lipophilic or it is hydrophobic. So now you see that when you are going to have the solvent, this particular lipophilic part will expose itself towards the solvent, and what can happen is that small size cations like lithium can very effectively get encapsulated into this particular host. And you can see that the overall shape of this host is a sphere. The overall shape of this host resembles like a sphere, and that is why this is referred to as a spherand. And this is also very, very specific to lithium. This is the interesting thing and a very important property about this host, because you can see here that, as was proposed by Donald Graham, he wanted to make converging binding sites towards the central binding pocket. So already in this hexa host, hexa related compound, 3 oxygens are already pre-organized. They have the converging binding sites, and 3 oxygen atoms in the bottom are already rigidly pre-organized. All that has to be done is the metal has to simply come and sit there and encapsulate itself very, very tightly. So it is very, very specific for lithium. Overall shape is spherical in nature, and this is referred to as a spherand, and this was found to display extremely strong affinity towards lithium plus, and the selectivity was also. So we need to have excellent activities and selectivity for certain metal ions. So in this regard, lithium ion displays the maximum selectivity for this particular spherand like arrangement. Larger size cations like potassium and sodium ion are not able to fit into this small size which is created by this highly pre-organized host, and therefore they don't undergo host gas complexation. So this class of ligands is referred to as the spherands. And then what was observed is that if you replace this oxygen, so when you replace the oxygen with fluorine, or say you replace it with it now becomes a carbon fluorine bond, then the complexation with the corresponding complexation with the corresponding cations drops. Then there is a drop in complexation. So it is very, very specific to this particular lithium ion that this activity takes place. Now let us go and look at some other properties of the crown ether complexes. So overall, after looking at potends, corends, cryptands and spherands, and the fact that the Nobel Prize was given to all the people who were associated with this work, what came out was that the crown ether is a very interesting class of compounds. and people were interested to look at the properties and the applications of crown ethers. We did look at some of these aspects in the previous lecture. Now we would like to go a bit deeper into the applications of crown ether ligands. So to start with, the crown ethers, again, these are soluble in a wide range of solvents, from water to alkanes, and they have got the right balance of lipophilicity and hydrophilicity. So when you look at the right balance of lipophilicity and hydrophilicity, so the polar content and the non-polar content has got the right balance. And you know, the partition coefficient, which is measured in octanol water system, is 0. That means it has got a perfect balance between lipophilicity and hydrophilicity. That means it represents a very balanced polar and non-polar surface to any solvent with which it is going to interact. So because we know that solvation has got a very important role in host gas complexation, it is very important that what is the conformation of this particular crown ether in different solvents. So we can have polar solvents and we can have non-polar solvents, like we can have hydrocarbons, or we can have polar solvents like chloroform, ethanol, methanol. And is the conformation of the crown ether same or different in different solvents? So it has been observed that crown ether is flexible in nature. So although it is a cyclic ligand, it is flexible in nature. Let us see what are the different conformations it adopts in different kinds of solvents. So this is my 18 crown 6, the ether. So 1, 2, 3, 4, 5, 6, and we have got the 12 carbon atoms, so total 18. And you can see here that in this case it is the non-polar part which is exposed, and the polar part is in the interior. So this is the interior, which is polar, and the exterior is the hydrophobic part, or you can also say the lipophilic part, which is the exterior. So if you were to actually dissolve this compound, for example in non-polar solvent, like for example in oil or in some hydrocarbon, then this is the conformation in which the 18 crown 6 will exist. And this is something similar to a drop of water in oil. So because oil is a non-polar medium, and this has got a balance of hydrophilicity and lipophilicity, so naturally the lipophilic part will present itself to the medium oil which is in its vicinity, and that is what will be exposed in oil. However, the polar part is in the interior, so it will be representing a polar environment, which is simply like having a small amount of the polar environment in an otherwise non-polar environment. That is something which we can say resembles a drop of water in oil. On the other hand, if we were to look in polar solvents, it now presents a hydrophilic exterior. So how does it present that? Let us see the conformation now. So, here we can see and here you can see the lone pairs. So, the lone pairs are now exposed. This is the hydrophilic exterior and the lipophilic interior. The hydrocarbon part or the non-polar part is now pushed inwards, such that the lone pair parts, the more polar parts, are now exposed, and this is called the hydrophilic exterior, and it has got a lipophilic interior. And this is something which is similar to a drop of oil in water. So, if you add a drop of oil then in water, so water definitely is the much more polar environment, and therefore this particular molecule will only expose the polar parts, so that there are nice hydrogen bonding between the polar solvent and the oxygen lone pairs, and this particular crown ether 6 is extensively solvated and is stabilized in the polar solvent. So, you see that this particular there exists a equilibrium between these two conformations depending upon what is the polarity of the medium. If you have a highly polar medium, then this particular conformation is stabilized. If you have a non-polar medium, then this particular conformation is present in abundance. And which is the conformation which is available for cation complexation? It is this particular cyclic conformation with the hydrophobic exterior or the lipophilic exterior that is available for complexation. In this case, the oxygen atoms are exposed outwards, and therefore this is not available for complexation. So, it is important to keep in mind that when we are going to study the host case complexation behavior, the correct conformation is available for binding. Mostly people would like to exploit this conformation where the oxygen lone pairs are directed inwards and the exterior is hydrophobic. So, now let us look at the applications of crown ethers as phase transfer catalyst. This is a case of nucleophilic substitution, and table 1 where the A can be acetate or it can be chloro compound, and this reaction is done in the presence of added crown ether. And what has been observed is the following: the reaction half-life in hours. So, when we have the crown ether, it is 685 hours. So, that depends on the type of crown ether. So, when we have none, it is 685 hours. When it is 18 crown 6, the time drops to 3.5 hours. When it is dibenzo 18 crown 6, it becomes 9.5 hours, and when it is dicyclohexyl 18 crown 6, the time is 1.5 hours. So, we can see here that the reaction time is dramatically affected by the presence of crown ethers. So, in the next class we will now look at the mechanism of this phase transfer catalyst and how the presence of the crown ether modifies the environment, the reaction environment, such that this reaction proceeds at extremely fast rates. Thank you.